The Pearl Harbor attack on December 7, 1941, had ended 6 hours earlier, but Lieutenant Colonel Hugh J. Casey remained motionless at his steel desk in a Honolulu headquarters. Before him lay the Pacific theater maps, and he couldn't turn away. The smoke from the burning harbor drifted past his office windows, carrying the acrid smell of burning aviation fuel and twisted metal. Red pins dotted the map like a spreading rash. Wake Island, Midway, Guadalcanal, dozens of coral atolls and jungle clearings where America would desperately need airfields if there was any hope of fighting back across 6,000 miles of ocean. Casey pulled out his slide rule. The numbers had to be calculated, no matter how brutal the results. Each concrete runway demanded 40,000 tons of cement, sand, and aggregate. He would need 300 skilled construction workers, 45 days minimum to build it, and that assumed perfect weather with no enemy interference whatsoever. His pencil traced down the list of strategic positions, multiplying by the projected timeline. The mathematics refused to be kind. At current construction capacity, the Army Corps of Engineers could complete perhaps 12 major airfields in a year. Yet the Pacific held over 60 critical positions where air power would determine victory or defeat. When his aide, Major Robert Stevens, entered with fresh intelligence reports, the situation only grew grimmer. "Sir, the Navy estimates we'll need operational airstrips at 37 forward positions within 18 months to support Admiral Nimitz's offensive plans." Stevens set down the folder and glanced at Casey's calculations, already understanding the implications. How many can we realistically build in that time frame? Casey tapped his pencil against the map. 18, maybe 20 if we're fortunate with supply convoys and if the Japanese don't interfere with our construction sites. The implication hung in the air like smoke. America would lose this war because it couldn't build runways fast enough. By February 1942, Casey's worst fears were materializing across the Pacific theater. The Baton Peninsula evacuation became a nightmare of abandoned construction projects. American engineers had destroyed their half-completed concrete runway rather than let it fall into Japanese hands. 6 weeks of grueling labor, 200 tons of precious concrete shipped 8,000 miles from California, reduced to rubble by Army demolition charges when the Japanese advance moved faster than construction crews could work. Field reports told the same devastating story everywhere. On Wake Island, Marine engineers had poured concrete foundations for a bomber strip when the Japanese assault began, leaving the runway existing only in blueprint form when the garrison surrendered. At Clark Field in the Philippines, a massive concrete expansion project lay 70% complete, rendered useless without the final month of finishing work that would never come. The pattern was shattering and consistent. Concrete construction demanded perfect conditions, stable supply lines, a secure perimeter, uninterrupted work schedules. War provided none of these luxuries. Traditional runway engineering, perfected during 2 decades of peacetime airport construction, proved catastrophically unsuited to combat conditions where strategic positions changed hands weekly or even daily. Casey found himself questioning everything his West Point engineering professors had taught him about airfield construction. They had drilled into him that runways must be permanent, stable, and built to withstand decades of heavy aircraft operations. But what good was a runway that took months to build when battles were won or lost in days? What value did permanent construction hold when forward airfields might be abandoned within weeks as military lines shifted? Standing in his Manila headquarters before the final evacuation, Casey wrote in his operational log with frustration bordering on desperation, "Concrete runways are a peacetime luxury we cannot afford. The perfect has become the enemy of the good, and the good has become the enemy of the possible." The entry would prove prophetic, though Casey had no solution to replace the construction methods that were failing so spectacularly. 8,000 miles away in Pittsburgh, Gerald G. Grulich was reading Aviation Week during his lunch break in the Carnegie Steel Company cafeteria. The February issue featured a grim article about runway construction delays hampering American offensive operations. Grulich studied the accompanying photographs of abandoned concrete pours and half-finished airstrips, then pulled out his ever-present notebook and began sketching. His engineering mind immediately grasped the fundamental problem. Concrete runways were monolithic structures. They either worked perfectly or failed completely. There was no middle ground, no way to build them incrementally or repair them quickly under combat conditions. But what if runways could be assembled like bridges? What if individual components could be manufactured in American factories, shipped anywhere in the world, then connected together like giant steel puzzle pieces? Grulich's pencil moved across the notebook page, drawing rectangles with carefully spaced circular holes. His colleagues at the neighboring table noticed his sketching and leaned over curiously. "Jerry, what are you designing now?" asked Tom Morrison, a structural engineer who had worked with Grulich on several Pennsylvania railroad projects. Grulich looked up from his calculations. Airplane runways made from perforated steel sheets that lock together. He showed Morrison the sketch, rows of interlocking panels, each measuring 10 feet by 2 feet, with precisely engineered holes distributed across their surface. Morrison laughed so hard he nearly choked on his sandwich. "Jerry, airplanes need solid surfaces, not Swiss cheese. You can't land a 15-ton bomber on metal sheets full of holes." The entire cafeteria table joined Morrison's laughter, but Grulich continued his calculations unfazed by their skepticism. That afternoon, alone in Carnegie Steel's metallurgy laboratory, Grulich began the load distribution mathematics that would change warfare forever. His slide rule clicked steadily as he calculated stress patterns across perforated steel surfaces. The conventional wisdom was dead wrong. Holes didn't weaken steel structures. Properly engineered perforations actually increase strength by redirecting stress loads more efficiently than solid sheets. Every structural engineer understood this principle in bridge design, but no one had applied it to runway construction. By evening, Grulich had filled 12 pages with calculations proving that his perforated steel planking could support aircraft weighing up to 20 tons while using 60% less material than solid steel sheets. Each panel would weigh just 66 pounds, light enough for 2 soldiers to carry, yet strong enough to handle repeated landings by the heaviest American bombers. The mathematics were irrefutable, even if they contradicted everything the aviation industry believed about runway requirements. Grulich closed his notebook and stared out at the Pittsburgh skyline, where Carnegie Steel's blast furnaces painted the winter sky orange. Somewhere in the Pacific, American pilots were dying because they lacked forward airfields. The solution lay in his calculations, waiting for someone with enough authority to trust mathematics over conventional wisdom. On March 15, 1942, Gerald Grulich stood before a blackboard in Carnegie Steel's main conference room, facing 12 of the company's senior engineers and 3 Army procurement officers who had driven up from Washington. His perforated steel runway prototype lay on the conference table, a single 10 by 2-foot panel weighing exactly 66 pounds. Its surface was punctured by 384 precisely machined holes arranged in a mathematical pattern that defied conventional engineering wisdom. "Gentlemen, load distribution across perforated steel follows the same principles as I-beam structural design," Grulich began, his chalk moving across the blackboard in steady strokes. "These holes don't weaken the steel. They redirect stress loads more efficiently than solid plates." He drew force vectors radiating through the perforated surface, showing how weight distributed through the whole pattern rather than concentrating at impact points. Each panel can support 75 pounds per square inch, which means a 15-ton bomber creates a safety margin of nearly 3 to 1. Major William Harrison, the lead Army procurement officer, studied the prototype skeptically. He had spent 2 decades overseeing concrete runway construction projects across the continental United States, and Grulich's proposal violated every principle Harrison considered fundamental to aviation safety. "Mr. Grulich, I appreciate Carnegie Steel's innovative spirit, but we're discussing aircraft operations, not bridge construction. Pilots need solid, stable surfaces. This looks like industrial grading." Grulich anticipated the objection. He had spent weeks refining his presentation, knowing that military procurement officers would resist any departure from proven runway specifications. "Major Harrison, allow me to demonstrate the load characteristics." Without waiting for permission, Grulich climbed onto the prototype panel and began jumping up and down. The steel flexed slightly but showed no signs of structural stress. "I weigh 170 pounds. This panel is supporting my full weight across 2 square feet of surface area, roughly equivalent to the pressure a B-25 bomber wheel exerts during landing. The demonstration failed to impress Harrison. Mr. Grulich, a B-25, weighs 15 tons and lands at 90 miles per hour. Your personal weight test hardly simulates combat landing conditions. Harrison's tone carried the authority of someone who had witnessed multiple runway failures during his military career. Furthermore, perforated surfaces would collect debris, create drainage problems, and provide insufficient traction for aircraft tires during wet weather operations. Grulich had prepared for these technical objections. He flipped to a new page in his engineering notebook, revealing detailed calculations about surface friction coefficients and drainage characteristics. Actually, Major, the perforations improve drainage by allowing water to flow through the surface rather than pooling on top. As for traction, our laboratory tests show that steel provides superior grip compared to concrete, especially during rain operations. The Army officers exchanged skeptical glances. Captain Douglas Wheeler, Harrison's technical aide, voiced the concern that dominated military thinking about runway construction. Sitting across the conference table, Mr. Grulich faced skepticism that no mathematical equation could easily overcome. Even if your calculations prove correct, one of the officers said, we cannot gamble with bomber crews. Aircraft safety in a war zone demands proven solutions, not theories that haven't been tested under fire. Concrete runways have served us faithfully for 2 decades. Why risk experimental materials when established methods work? Grulich watched the moment slipping through his fingers. These military men were trained to eliminate uncertainty, to favor the familiar over the untested. Their caution was understandable, even logical, but it stood between innovation and necessity. Yet Grulich possessed knowledge these officers did not. Reports from Lieutenant Colonel Casey in the Pacific had circulated through the War Department, revealing a troubling reality. Conventional concrete construction was collapsing under combat conditions. The system that had worked for 20 years was failing when it mattered most. Grulich seized the opening. Captain Wheeler, how long does your current concrete runway construction actually take in the field? Wheeler flipped through his briefing folder, then answered. Specifications require 45 days minimum under ideal circumstances. Construction schedules rarely remain uninterrupted during combat operations. Weather delays, supply problems, enemy activity all compress the timeline further. That's precisely my argument. Grulich pressed forward. These perforated steel panels are built in American factories, transported anywhere globally, and assembled into functional runways in mere hours. No mixing concrete, no waiting for it to cure, no need for heavy construction equipment or specialized crews. 2 soldiers can carry each panel. The interlocking system uses only basic hand tools. Speed and simplicity, that's what modern warfare demands. Major Harrison shook his head, preparing to dismiss the proposal. If assembly speed means nothing when runways fail on first landing, Grulich, our pilots need dependable surfaces, not experimental systems that might give way under real operational stress. Harrison gathered his papers. Your proposal enters our technical review. The Army Corps of Engineers will likely demand extensive testing before considering any change to established runway standards. The officers shook hands formally and departed. Grulich watched their vehicles disappear, understanding that his steel panels would vanish into military bureaucracy unless someone with genuine authority recognized what he'd accomplished. Wartime procurement channels moved with glacial slowness when innovation contradicted everything engineers had built their careers upon. Then, 2 weeks later, salvation arrived from an unexpected direction. Captain John Thompson had recently transferred from the 805th Engineer Aviation Battalion to Wright-Patterson Field. When Grulich's technical specifications landed on his desk for review, Thompson recognized something the procurement officers had missed. Thompson possessed combat credentials that changed everything. He had flown P-40 Warhawks throughout the Philippines campaign, landing on surfaces that would have horrified any military engineer reviewing safety standards. His experience gave him perspective that theoretical caution could not provide. Grulich's mathematical calculations interested Thompson professionally, but more importantly, they addressed real problems Thompson had witnessed firsthand across the Pacific. He had touched down damaged fighters on coral beaches, jungle clearings, and bomb-cratered concrete that bore almost no resemblance to properly constructed peacetime runways. Yet those aircraft survived. Operations continued. Grulich's concept suddenly made practical sense. On April 2nd, Thompson drove to Pittsburgh. For 6 hours inside Carnegie Steel's testing facility, the two men examined prototype panels and discussed what combat aviation actually required. Thompson asked questions grounded in operational reality rather than theoretical specifications. How quickly could damaged sections be replaced? Could the system function with missing pieces? Would the interlocking mechanism survive repeated stress? Grulich answered each question through engineering analysis, but Thompson needed to verify something deeper. He positioned a 50-pound concrete block above the prototype surface and released it repeatedly, simulating the impact forces of aircraft landings. The steel flexed slightly beneath the strikes, absorbed the shock, and returned to its original shape undamaged. Thompson ran his hands across the perforated surface, feeling the craftsmanship. "I've landed on worse during combat," he said quietly. "This feels more solid than half the improvised strips we used in the Philippines." His endorsement carried authority that skeptical procurement officers could never match. Thompson combined combat experience, engineering training, and responsibility for airfield construction in the European theater. When Thompson submitted his technical evaluation recommending immediate field trials, military aviation officials finally possessed an authoritative voice supporting Grulich's concept. By May 15th, the Army authorized building a prototype runway at Wright-Patterson Field. Grulich's mathematics would finally undergo the ultimate test, supporting actual aircraft under operational conditions. Those initial landings would determine everything. June 23, 1942, brought Captain Thompson to the edge of a runway that existed nowhere in military engineering textbooks. 1,500 perforated steel panels stretched across Ohio grassland, each section locking to its neighbors through Grulich's interlocking hook system. The assembled surface resembled an enormous steel checkerboard, thousands of precise machine holes capturing the morning light. Thompson checked his watch. In 30 minutes, test pilot Lieutenant Robert Mitchell would attempt the first official military aircraft landing on perforated steel planking. The implications extended far beyond this single flight. Colonel James Devine, chief runway engineer for the Army Corps, had arrived from Washington carrying specific orders. Devine brought decades of successful runway projects to his record. Kelly Field in Texas, Hickam Field in Hawaii. Every project used concrete, steel reinforcement, construction timelines measured in months. The notion of landing heavy bombers on interlocking metal sheets struck him as fundamentally flawed, regardless of mathematical proofs. Devine examined the panels through field glasses with obvious concern. "I've witnessed experimental runway materials fail catastrophically," he said. "If this system collapses beneath a 3,000-pound trainer aircraft, imagine what happens when we discuss 15-ton bombers under combat conditions." Devine's skepticism reflected genuine responsibility for pilot safety. He had investigated too many runway failures resulting in aircraft casualties to treat unproven technology casually. Thompson understood his reservations but offered perspective from actual warfare. "Colonel, I've landed damaged fighters on surfaces that would shock peacetime safety inspectors. The real question isn't whether this meets peacetime standards. It's whether perforated steel provides better operational capability than concrete runways we cannot construct fast enough under combat conditions." Thompson gestured toward the assembled panels. These 1,500 sections were installed by 12 men in 8 hours. A concrete runway of equivalent length requires 300 workers and 6 weeks minimum. At 900 hours, Lieutenant Mitchell's North American AT-6 Texan appeared on final approach. The single-engine trainer weighed 3,000 pounds fully loaded, representing the lightest operational military aircraft in the inventory. If perforated steel could not support an AT-6, heavier bombers would be impossible. Mitchell maintained standard landing procedures, touching down at 65 miles per hour. When his wheels contacted Grulich's perforated surface, Thompson heard something distinctive, not the sharp crack of structural failure, but a resonant ping as steel flexed under load and returned to shape. The aircraft rolled normally for 800 feet before Mitchell applied brakes and stopped smoothly. "Surface feels solid as concrete," Mitchell reported. "No unusual vibrations, no structural movement detected. The perforations create interesting visual effects during landing, but aircraft handling remains completely normal." Mitchell taxied to the runway's end and executed a standard takeoff using the same perforated surface. The system performed flawlessly with no panel separation or surface deterioration. Devine remained cautious despite success. Captain Thompson, an AT-6 trainer, hardly represents the operational loads in combat theaters. "I need to see this handle aircraft that actually matter for strategic operations." His skepticism was professionally justified. Military decisions affected thousands of pilots. Rushing unproven technology into combat could produce catastrophic failures. Thompson anticipated this objection. "Colonel, I've arranged escalating load tests over the next 2 weeks. Tomorrow we test a B-25 Mitchell bomber, 15 tons gross weight, 90 miles per hour landing speed. If successful, we'll progress to fully loaded transports and eventually the heaviest bombers in our inventory." The B-25 test occurred June 25th under clear skies. Mitchell's bomber approached at standard operational speed, twin-right R2600 Cyclone engines throttled for landing configuration. Thompson watched through binoculars as the 15-ton aircraft contacted Grulich steel surface with significantly greater impact force than the trainer test. The perforated panels flexed visibly beneath the main landing gear, distributing concentrated wheel loads across multiple interlocking sections, exactly as Grulich's calculations predicted. "Runway performance excellent," the test pilot reported. "Surface provides adequate traction, no structural movement, aircraft handling normal throughout all ground operations." The pilot's professional assessment carried enormous weight with military evaluators who relied on aircrew reports to judge new equipment under realistic conditions. Devine's resistance began cracking as test results accumulated. His engineering training confirmed Grulich's mathematical analysis was fundamentally sound, even though it contradicted established runway construction practices. More importantly, reports from the Pacific Theater continued emphasizing desperate need for rapid airfield construction capability. Lieutenant Colonel Casey's urgent requests for alternative runway systems reached the highest levels of Army command, creating pressure for innovative solutions regardless of their departure from tradition. By July 15th, the Wright-Patterson trials had validated perforated steel planking for aircraft up to 20 tons. Test pilots reported consistently positive experiences across multiple aircraft types, from single-engine fighters to twin-engine medium bombers. The interlocking system showed no structural fatigue despite repeated heavy aircraft operations. Installation proved remarkably efficient compared to concrete construction timelines. The breakthrough moment came when Devine submitted his official technical evaluation to the War Department. Perforated steel planking performs in accordance with manufacturer specifications and provides acceptable operational characteristics for military aircraft operations, his report concluded. He recommended immediate procurement for field trials in active combat theaters. The man who had initially dismissed Grulich's system as impractical now championed its adoption based on objective engineering evidence. Carnegie Steel received orders for 50,000 perforated panels by August 1st. Production specifications called for 2,000 sections daily once manufacturing reached full capacity. The manufacturing process demanded absolute precision. Each steel panel needed exactly 384 perforations, drilled to specifications that left no room for error, then treated with galvanizing to shield against the relentless salt water and humidity of tropical deployment. One faulty section could compromise an entire runway when aircraft touched down at full combat weight. Grulich understood this completely, and he drove himself through 18-hour workdays to guarantee that every production step matched the exacting mathematics his design required. Moving from a laboratory concept to full-scale manufacturing unleashed unforeseen complications. Rivet specifications had to be strengthened, coating procedures needed constant refinement. Yet by September, Carnegie Steel's Pittsburgh plant was churning out perforated steel planking, fast enough to support massive military operations across every ocean and continent. That sketch on a lunch napkin was transforming into the backbone of American aerial dominance. October 8, 1942. Casablanca on the Moroccan coast. Captain John Thompson stood waist-deep in the Atlantic, watching cargo vessels unload the first combat shipment of perforated steel panels onto the beach. Operation Torch had started 72 hours before, and American forces needed working airfields immediately. Ground troops were pushing inland to face French defenders, and concrete runways would demand 6 weeks of construction that military schedules simply could not spare. German reinforcements were flowing in daily from Tunisia, and every hour mattered. Thompson's engineering battalion had trained for 2 months at Fort Belvoir on assembly procedures. But training exercises bore no resemblance to the actual chaos unfolding here. German dive bombers were targeting supply convoys. French artillery shelled the beach. Each panel measured 10 by 2 feet and weighed 66 pounds dry. But Atlantic spray and Moroccan sand transformed each one into a 76-pound burden that exhausted soldiers had to wrestle from the ship through heavy surf and across the beach. Those interlocking hooks that performed flawlessly in Ohio laboratories now stuck and jammed when salt corrosion and sand particles fouled the connections. "Sir, we have 800 panels on the beach and staged for assembly," Sergeant William Morrison reported, gesturing toward the orderly stacks of perforated steel arranged in precise patterns across the sandy terrain. "Our calculations show we need 1,500 sections to complete a 3,000-foot runway that can handle P-40 Warhawk operations." Morrison studied his field manual, matching PSP specifications against what the aircraft loads would demand. "Based on current unloading pace, we should have what we need by 6 o'clock tonight." Thompson reviewed his tactical map, noting the reconnaissance aircraft the Luftwaffe had been circling overhead since dawn. Intelligence indicated that German bombers, staged from Rabat, were readying an assault on the American beachhead. American fighters were desperately needed within 24 hours. Morrison started assembly work with the panels they had available. "We'll add more runway as additional material arrives, but I need at minimum 1,500 feet ready to operate by dawn." The actual assembly revealed both the system's remarkable advantages and the harsh realities of building under battle conditions. Gorelich's interlocking design permitted installation at remarkable speed. 2 soldiers could position and lock each panel in roughly 3 minutes using only basic tools. But North African sand created problems that Ohio laboratories had never encountered. Wind-driven particles infiltrated every connection, demanding constant attention to prevent panels from separating when aircraft landed and took off. The desert heat caused the metal to expand, loosening the interlocking hooks unless work crews maintained exact spacing standards. By 6 o'clock, Thompson's battalion had completed 2,000 feet of PSP runway, despite Stuka attacks that stopped construction repeatedly. The perforated surface appeared strange against the Moroccan landscape, a geometric steel carpet laid across sand and scrub. Local Arabs observed the installation with wonder, having only known aircraft operating from packed earth or concrete. The true test arrived at 6:30 the next morning when Major Robert Johnson approached the PSP strip in his Republic P-47 Thunderbolt. This 7-ton fighter represented significantly greater weight than previous trials, and Johnson's combat profile meant maximum fuel and ammunition, pushing the aircraft to its operational limits. Thompson tracked the landing attempt through field glasses, understanding that success or failure would reveal whether PSP could handle actual warfare rather than just peacetime tests. Johnson's Thunderbolt hit the perforated surface at 85 miles per hour, with the fighter's characteristic authority. The steel panels flexed noticeably under the main landing gear, producing metallic sounds Thompson recognized from Ohio trials. The panels held, no separation, no failure. Johnson rolled to a controlled stop within 800 feet. "Runway surface performs acceptably," Johnson reported over the radio. "Aircraft handling is normal, no vibrations or control difficulties." The Casablanca PSP runway opened for operations on October 10th, handling 12 P-47 sorties against German positions near Rabat. Each landing and takeoff vindicated Gorelich's calculations regarding load distribution and structural strength. More significantly, the rapid construction had delivered air support for American ground forces precisely when needed, avoiding the 6-week delay that concrete would have demanded. General Henry Arnold, commanding the Army Air Forces, learned of the North African success within 48 hours. Arnold's entire strategic vision rested on rapid airfield construction, allowing aircraft to operate from any location American forces secured. The PSP system promised revolutionary capability, transforming any stretch of terrain into a functional airfield, whether coral atolls in the Pacific or farmland in Europe. Arnold authorized massive production expansion, ordering 500,000 panels for Mediterranean and Pacific campaigns. Carnegie Steel's Pittsburgh operation went to 24-hour production schedules, employing 3,000 workers focused exclusively on perforated steel manufacturing. Quality control grew more difficult as volumes increased, yet Gorelich's design specifications proved robust enough to survive minor manufacturing imperfections. December 15th brought the ultimate affirmation when Admiral Chester Nimitz's Pacific Fleet began using PSP airfields in Operation Cartwheel, the methodical push toward Japanese positions in the Solomon Islands. Guadalcanal's Henderson Field received PSP extensions that doubled its capacity within 72 hours, converting a marginal fighter base into a major bomber staging ground. The work required no concrete, no specialized machinery, and no extended curing that Japanese artillery could target during construction. By year's end, 47 PSP airfields operated across 3 combat zones from North Africa to the Southwest Pacific. Total runway length exceeded 150 miles of perforated steel, accommodating everything from single-engine fighters to 4-engine heavy bombers. The mathematical precision Gorelich had sketched in a Pittsburgh cafeteria was proving itself under the harshest conceivable conditions. Yet a more severe examination awaited. Pacific intelligence reports revealed that Japanese forces were developing new artillery techniques specifically designed to destroy American airfield construction. Concrete runways' permanence made them targets for systematic bombardment that could knock them out for weeks. PSP's modular structure offered theoretical repair advantages, but those advantages faced their supreme test under concentrated enemy fire, where failure could spell military catastrophe for thousands of Allied soldiers depending on air protection. January 22, 1944. Anzio, Italy. Captain Thompson crouched in a mud-filled crater 50 yards from the PSP runway that represented the sole lifeline for 36,000 trapped Allied soldiers on a narrow coastal strip. German 88mm shells had fallen relentlessly for 18 hours. Systematic bombardment aimed at shattering the perforated steel runway, enabling P-47 Thunderbolts to deliver essential close air support for the beleaguered beachhead. At 3:15 in the morning, a direct strike had obliterated 200 feet of runway, leaving a jagged gap that standard doctrine deemed impossible to repair under fighting conditions. Thompson studied the destruction through field glasses as another bombardment erupted around the airfield perimeter. 27 panels lay twisted and shattered, their interlocking hooks severed by the shockwave that had carved a crater 15 feet deep and 30 feet across. Conventional repair procedures demanded heavy equipment, concrete patches, and minimum 48-hour waiting periods. None of those resources existed on a contested beachhead where Germans held the surrounding heights and observed every Allied movement. Sir, P-47s are inbound at 6 o'clock with close support missions for the British 1st Division, Sergeant Morrison called, voice barely audible beneath continuing artillery fire. Without air cover, General Lucas believes German counterattacks will overrun our forward positions by nightfall. Morrison's assessment captured the brutal calculus of beachhead survival. Allied ground forces could maintain their defensive line only so long as American fighters kept German artillery and armor suppressed. Thompson had prepared his crews through exactly this scenario during PSP training at Fort Belvoir. Yet reality clashed violently with theory when German rockets screamed toward repair operations and German fighters strafed the supply trucks attempting to bring replacement panels forward. Gorelich's modular design theoretically permitted quick section replacement, but only if repair crews could work without constant enemy interference. Morrison organized 12-man teams with replacement panels staged at the crater's edge. Thompson issued orders, Glancing at his watch in the pre-dawn darkness, German observers on Monte Cassino can see everything we do down here, so we'll work during the brief gaps between their bombardment cycles. Experience had taught Thompson that successful repair required timing synchronized with German firing patterns, not continuous non-stop construction. At 4 o'clock, Thompson's first repair team sprinted across the exposed runway surface, carrying replacement PSP panels toward the bomb crater. German artillery maintained consistent schedules throughout the night, with roughly 12-minute intervals between major bombardment waves. This narrow opening provided just barely enough time to position and connect 4 panels before the next barrage forced crews to scatter and seek shelter. The interlocking hook system proved its worth under the most extreme combat imaginable. Each panel weighed 66 pounds, light enough for 2 soldiers to move quickly across broken ground, yet strong enough to withstand repeated aircraft passes once properly connected. Critically, individual damaged panels could be removed and swapped without affecting adjoining sections, something concrete runways could never accomplish. Thompson's crews moved with mechanical efficiency despite the devastation surrounding them. Artillery shells detonated 50 yards distant, throwing shrapnel through the air, yet soldiers methodically positioned new panels into the crater, aligned the hooks and secured connections with standard field tools. The perforated steel that had seemed alien during North African operations now felt dependable and solid under Italian combat. By 5:30, the repair teams had installed 18 replacement panels, shrinking the runway gap from 200 feet to approximately 60 feet. Thompson knew that P-47 pilots could easily clear 60 feet during takeoff and landing. However, complete restoration demanded 9 additional panels to return full capability for heavier machines like B-25 Mitchell bombers. The decisive moment arrived at 5:45 when German artillery observers spotted the ongoing repairs and redirected their fire directly onto the PSP runway. Thompson watched as 88mm shells exploded across the partially repaired section, sending steel fragments and debris scattering. Standard runway materials would have suffered total destruction from this concentrated fire, demanding weeks of reconstruction using equipment that did not exist. Instead, Gorelich's modular system absorbed the punishment with extraordinary resilience. Direct hits completely destroyed individual panels, but surrounding sections stayed intact and fully operational. The interlocking system distributed shockwaves across multiple panels, preventing catastrophic failures affecting entire runway sections. Critically, hit panels could be immediately disconnected and swapped with spare sections that Thompson's supply teams had positioned around the airfield perimeter. At 6 o'clock precisely, Lieutenant Robert Johnson's P-47 Thunderbolt appeared on approach, despite continuing German artillery. Johnson understood that the runway remained incomplete, but his close support mission was vital for Allied ground forces facing renewed German assaults across the beachhead. Thompson held his breath as the Thunderbolt descended onto the repaired PSP surface at standard landing speed. Runway surface is operational, Johnson reported via radio after executing a perfect landing and taxiing to his revetment. Panel connections holding solid, no unusual vibrations during rollout. Within 15 minutes, Johnson had refueled, rearmed, and launched again, using the same repaired runway, demonstrating that PSP maintained continuous combat capability under direct enemy fire. The Anzio experience confirmed PSP as fundamental to Allied air operations. By February 1st, Thompson's battalion had repaired the runway 7 times following German strikes. Each time they restored full capacity within 4 hours, using replacement panels brought by LST landing craft. Accumulated damage would have permanently wrecked any concrete runway, but Gorelich's modular approach permitted unlimited repair cycles, constrained only by spare panel supply. General Mark Clark's 5th Army headquarters received comprehensive reports documenting PSP performance, emphasizing rapid repair capabilities that sustained air support through critical ground operations. Clark concluded that perforated steel planking had fundamentally transformed air and ground operations by eliminating fixed runway vulnerability to artillery bombardment. The Anzio success reached the highest Allied leadership within days. General Dwight Eisenhower, Supreme Commander for Operation Overlord, studied PSP specifications with focused attention as his planners determined airfield requirements for the Normandy invasion. Eisenhower's strategy demanded immediate air support for amphibious operations, requiring operational runways within 24 hours of initial landings, rather than weeks for concrete construction. The mathematical precision Gorelich had calculated in a Pittsburgh cafeteria was proving crucial not merely as engineering, but as strategic military capability reshaping how warfare integrated air and ground power across global theaters. One civilian engineer's determination to challenge conventional runway construction wisdom had created capability revolutionizing how modern warfare combined air power with ground operations across every combat zone worldwide.